All right, now let's take a look at how we can integrate both rotational kinetic energy as well as linear kinetic energy and gravitational potential energy. So in this exercise, we have a hoop that rolls without slipping down a 5-meter high hill starting from rest. So basically, what we have given to us here is that there's a hill here, and the height of this hill is 5 meters. And there's a hoop up here, a thin-walled hollow cylinder, we can call it, and it rolls down, and then it gets down over here, and we want to know how fast it's traveling, like its linear velocity, when it gets down to the bottom. What is the final velocity here, assuming that it starts out at rest up here? No, it does start. They actually tell us that it starts from rest. So v naught is equal to 0, and it can't slip. If it slips, then we have some friction, and the work done by friction here. So we have to be very careful here that it's actually not slipping. So it has to tell us here it's not slipping. But I won't give you anything that does slip because that's a bit more complicated. How fast would it be traveling once it gets to the bottom? And so we can actually just use conservation of energy, right? If I establish a datum down here where this is the height is equal to 0, actually let me say find v at the bottom. That's what we're looking for. And if I set the height equal to 0 here, then I know that I have some gravitational potential energy up here, and then I have no gravitational potential energy here. Actually, to be more accurate, we're really going to the center of it here, so really the height is set equal to 0 here, and then it goes up to our maximum height is up here. But effectively, the change in height between these two green lines is the same as the change in height between here and here. It's still 5 meters. It drops 5 meters. So we can still use this bottom datum down here. And so we have only potential energy, gravitational potential energy at the top, and then we'll have only kinetic energy at the bottom, right? And so using conservation of energy, conservation of mechanical energy, we have here the mechanical energy at the top is equal to the mechanical energy at the bottom. So this means that we have mgh, because we only had gravitational potential at the top, is equal to kinetic energy at the bottom plus the rotational kinetic energy at the bottom, right? Because now we need to consider the fact that we have not only is it translating down, but it's also rotating, right? So this is all. We just need to make sure to add this piece. Oops. We need to make sure to add this piece in as well. Okay. All right. So we have mgh is equal to linear kinetic energy is just 1/2 mass times speed squared, and it's just the mass of the hoop, and the speed is actually the speed of its center of mass, which it's just how fast this middle moves down over here like this. And that's why I said, really technically it's the height difference between these two, but that's the same as the height difference between the bottom and the bottom. And so that's 1/2 mv squared, and then plus the rotational kinetic energy is 1/2 I omega squared, right? So we need to know what I is, right? But if there's a hoop, if you look at the table of moments of inertia, then we have the moment of inertia of a hoop is equal to just mass times radius squared, right? Because it's actually the same equation as a point mass, because all of its mass is distributed equal distance from the center, right? So it actually works out to be the same as a point mass. So let's see, we can write this out then as mgh is equal to 1/2 mv squared plus 1/2 of mr squared omega squared. Which actually, that gets rid of the mass in all of these. Mass is gone. It's in all three of these terms. And so we have GH is equal to 1/2 v squared plus 1/2 r squared omega squared. But, I don't have, I'm looking for v, right? This is okay, I have g, I have h, I have r. I believe we were given r, right? Oh, we weren't even given r. We're not given very much information. We're just 5 meters high hill. That's it. So, seems that we have v is unknown, r is unknown, and omega is unknown. We have 3 unknowns. But there's a relationship. Remember, there's a relationship between the linear speed and the rotational speed, right? And the linear speed of a point on the edge would actually be the linear speed of the center as well. And so we can actually just find the linear speed. We can write it out here as v equals r omega. Or I don't want to replace v with r omega. I want to replace omega with v over r. So if I make this substitution into here, then we have GH is equal to 1/2 v squared plus 1/2 r squared times v over r squared, which then this r squared will cancel with this r, which gets squared, right? And we got rid of r. We got rid of one of our unknowns. Actually, we got rid of 2 of our unknowns, the omega and the r, at the same time. So GH is equal to 1/2 v squared plus another 1/2 v squared is what this comes out to. And adding a 1/2 v squared plus another 1/2 v squared, that's a whole v squared, right? So this whole thing reduces down to GH is equal to v squared. All that. And so we get v is equal to the square root of GH. Which, if you remember back, when we just had something sliding down and we said mgh was equal to 1/2 mv squared, then it came, sorry about that, this is mgh, when gravitational potential energy was equal to kinetic, when we had a box sliding down or something, then we had v was equal to the square root of 2gh, right? It was actually going faster on this frictionless surface, but we had to have a frictionless surface, right? It always had to be like a block of ice sliding down an ice ramp or something. If it's rolling down, it's going to end up going a little bit slower because some of the energy went into just getting it to roll, right? And actually, this depends on the shape. This is not always for everything that rolls down the hill or any hill. We have to take into consideration what is the shape, obviously, right? So it's a hoop. A solid disc would obviously be different than a hoop as well. So because that rotational inertia is different. So you have to take this into consideration, but it's going to go slower than something that is just sliding down on a frictionless surface. But in reality, we don't have frictionless surfaces, so the rolling thing will go down faster because this one subtracts actually a lot of friction out. But for our exercise, we have here this final speed of this hoop rolling down the hill without slipping is the square root of 9.8 times the height of the hill, which is 5 meters, and this comes out to just 7 meters per second is the speed at the bottom. So even if it looks like you have absolutely no information, just start writing out what you do know, and you might realize that you don't need very much information. All we needed to find this, based on our assumptions, was the height of the hill and the shape of the object rolling down.